we should start because my watch is now timed with satellites, so it must be accurate. So welcome everyone to our weekly colloquium. Just wanted to mention one brief thing, which is last week I took part in a discussion of the decadal survey that we have in astronomy once every decade. So the next one is 2020, and the preparations are starting. But the important news, as far as we are concerned, is that the gravitational wave astrophysics is very much in the minds of many people, both in terms of NASA taking part in LISA, which is going to be launched in 2032 at the moment, according to current plans. And that would be sensitive to much lower frequency gravitational waves than LIGO. So we should be able to see a lot of mergers with much higher significance, but this time of supermassive black holes at the centers of galaxies. So that would complement LIGO. There would be also events where they start in the LISA band at low frequencies when the two compact objects are at large separation, and they enter into LIGO later on. So that would be another interesting type of sources where you monitor the source from early times to late times. So LISA is supported by NASA, and NASA is putting a lot of effort into the technology development related to LISA over the next decade. So that was mentioned by Paul from NASA, a very important person there. And in general, the decadal survey will highlight the gravitational wave astrophysics. NSF needs to find ways of transferring funds from, right now, LIGO was funded from the physics budget, but it's clear that it's now an observatory. We have more than one event, and we are looking at the sky. There is no reason to think that observatories should only look for photons. So it is an observatory, and it will become part of NSF astronomy eventually. All of this comes together in the next decadal survey, and it will prove to be a very exciting next decade in astronomy, thanks to LIGO. So that's my brief 10 cents. And for today,
yes, today we're happy to have Feraz Azhar. Feraz got his PhD in philosophy in University of Cambridge and a PhD in theoretical physics from University of California, Santa Barbara. And he works at the intersection between philosophy and physics, especially focused on connection between a black hole and early universe cosmology. And he's now a BHI fellow in philosophy here. And today we'll talk about inflationary trajectories, an effective theory approach.
Thank you. Thanks so much for the introduction. It's a pleasure to be here. It's been a wonderful couple of months while I've been here. It's been such a pleasure that I haven't, in fact, been able to get to complete this paper, which I was hoping to have done as of sort of 5 minutes before giving this talk. But hopefully it will be coming soon on the archive. This is work that's been done in collaboration with David Kaiser at MIT, and was started and mostly done while I was a visiting student there, and also is in my dissertation, which was completed earlier this year. So this is work that is not ostensibly about black holes. It's about sort of one side of my interest, and very often this cosmology. And in particular, I'll be worrying about inflationary trajectories and a particular approach to thinking about inflation, which is a little more general than the way that people typically think about this, or at least were typically thinking about this prior to sort of 10 years ago. Okay, so what I thought I would do is I would tell you a little bit about the sort of prehistory of the motivation for the project, highlight some conceptual issues that arise before launching into some of the calculations that we've been doing. So just so that we're all on the same page, inflation is a brief period of accelerating expansion, so the second derivative of the scale factor is greater than 0, and it's thought to have solved fine-tuning problems with the standard Big Bang model. So this is one of its purported successes. It's not necessarily the reason why people are excited about inflation. Those who are in fact excited about inflation, it's not necessarily the reason why they are excited about it, but it's certainly a statement that it makes. And what was noticed early on was obviously the idea that inflation is a solution to these fine-tuning problems, if it's the case that it's not fine-tuned itself. And there was early work that was done, so there's a review article there by Paolo in 1992, and a more recent review of the initial conditions problem in the context of inflation by Brandenburger And what I want to do is sort of point out a few conceptual issues. So one is arises from the question of what it is that we mean by initial. And there's sort of two things that we could worry about when we talk about initial conditions, which relate to what it is we mean by initial. One is that we think that inflation begins immediately after the universe emerges from the Planck era, so at 10 to the minus 43 seconds after the Big Bang, in which case initial conditions of inflation refer to the conditions of the universe at that moment in time. Or there's a delay after the universe emerges from the Planck era before inflation begins. And this is the kind of idea that's been supported by by the Planck data of late. So these plateau type models which kick in at much lower energy scales than Planck energy density. And then initial conditions can refer to one of two things, either conditions at the Planck time again, or to conditions just before inflation itself begins. So to part B, the second way of thinking about what initial conditions mean in this context treats inflation as an effective field theory. Right? So a theory which kicks in at some energy scale, and the description of the universe occurs via the theory at that energy scale. Irrespective of how you think about initial, there are questions about how inflation depends on these initial conditions. And there are two sort of general ways to think about them. Namely, you can worry about how finely tuned initial conditions need to be to lead to sufficient amounts of inflation, so 16-fold inflation, for example, starting from a homogeneous and isotropic cosmology. So RW stands for Walker, and refers to spatially homogeneous and isotropic cosmologies. Or you can worry about the case where this is not the case. So how is it, how finely tuned are the initial conditions in cases where your universe is not homogeneous and isotropic? And the second way of thinking about things is clearly the larger challenge. There's lots of ways things can be homogeneous and isotropic. And it turns out that there's a lot of work that's been done, particularly recently in the last couple of years, numerical work, full sort of 3 plus 1 dimensional numerical work which builds in anisotropies and looks at the onset of inflation in that context for specific potentials, V of phi. And the consensus is that these large field inflation models, so where the excursion of the scalar field is large in some sense, are more robust to sort of anisotropies and continuities than the small field models, and there's some references that we can.
Now, when the field exceeds the Planck mass, is that an issue because we don't have quantum theory?
Yeah, I mean, I think they allow for these sorts of.
Do we feel confident that effective field theory is valid for those?
I think you can write it down for these sorts of. I mean,
there is no conceptual issue.
There's no conceptual issue, I don't think. No, the energy scale that the effective field theory kicks in at is right a couple of orders of magnitude at least lower than this. But the effective clock that sits in the background, well, you'll see how the clock sort of kicks in, but you can rig things so that this is not such an issue as effective field theory approach. One of the issues, one of the problems with inflation that people have pointed out is, in fact, it's a plethora of...
Weren't those super Planckian bevs, that was something that was needed when we thought R might be large, and then when that experiment went away, has that also ceased to be an issue? Or?
You're saying that...
Well, at one point we thought we needed a large R.
Yes. Right, so some of these...
but now it doesn't look like that, and so we don't have to worry about super Planckian bevs. Isn't that how it works?
Well, you can have these super Planckian bevs for these plateau type models which have low values of R.
Yeah, I think that's what people favor now, actually.
Right.
But
These Starobinsky type models. So one of the issues with inflation that people criticize is the fact that it's particularly flexible, that there are a sort of plethora of potentials that you can write down, which you can fit to data. This effective field theory of inflation approach that I'm going to talk about tries to abstract away from these specific cases. So it looks at situations where you sort of have a general clock in the background that doesn't set down a specific potential. And what we thought we would do is look at inflation from this point of view and look at, in particular, dynamical trajectories in that context. So sort of marrying this effective field theory approach together with the dynamical systems analysis to look at general flows for these single clock descriptions to see what sort of general statements we can make about these flows. And then along the way, we're able to characterize what are essentially priors for such general FRW cosmologies to flow into inflationary states. And this is for initial conditions that aren't geared to trigger inflation. So this is the connection with the initial conditions problem. Although this sort of framework isn't necessarily set up to deal with the sort of strong version, the harder version of the initial conditions problem, because we're dealing with a spatially homogeneous isotropic universe to begin with. So some of the results are listed as follows. There are more, but this is what we're sort of settled on for now. You can show that in this sort of marriage of this effective field theory, this dynamical systems analysis, that the probability for inflation in the two simplest phase spaces can in fact be significant. If you include initial conditions such that subsequent flows are not compatible with the usual single-scalar-field realizations of inflation, and this can enhance the probability, so there are more initial conditions which can lead to inflation. And when the single clock, which is running in the background, which can be made to correspond to the usual single-scalar-field realization, then there's a universality with respect to the potential, which describes the dynamics. You can write down a sort of single functional form for V of phi that is in effect working in the background. So I'll describe how that arises as well. So this effective field theory equation was written down about 10 years ago, and the idea, you can read about it in that paper that I've mentioned at the top there, but the idea is to write down the most general action which respects symmetries of an inflating universe. So when you have a clock which is counting down time to the end of inflation, you sort of break time translational invariance, and you have three-dimensional spatial diffeomorphisms which can depend on time. So you have time-dependent spatial diffeomorphisms as your basic symmetry around which you construct this action. And they're constructed in unitary gauge, which is a particular slicing, such that the fluctuation in the clock vanish. Then the version of their action that will be of interest to what I'm talking about here affects a fluctuation expansion about sort of FRW models, and a metric derivative expansion as is usual in these effective field theory approaches. And you end up with an action which looks like you see displayed there. There are sort of two functions of time, L of t and C of t, and a term k00 plus these delta s plus delta s, which includes all these higher order terms which we're going to ignore, because we're just sort of interested in the march of the background to inflation. So that functional form should look familiar for those of you who deal with sort of inflation with a single scalar field. If you look down here, then in unitary gauge, so when fluctuations in this clock vanish, you end up with two terms which can be mapped precisely onto the original effective field theory action. And we demand that, in fact, the FRW background around which we're expanding satisfies the Einstein field equation, so you end up with the usual Friedmann equations when you vary the action with respect to the metric.
You're ignoring spatial derivatives, just
exactly. So this is just.
But that's by construction.
That's by construction, and it's an important problem when you're worried about the initial conditions. So here we've sort of abstracted away from that. So you just have kinetic degrees of freedom, you just have potential degrees of freedom. They interact in such a way that you end up with this dynamical system. How do we construct this dynamical system? Well, we sort of use work that was set down in the context of an effective field theory of dark energy, so that paper is mentioned at the top there, and you treat, the idea is you leave L of t and C of t, these two functions of time which appear in the action, you leave them to be free, but subject to the Friedmann equations, and you ask, from a dynamical systems point of view, what sort of values of these functions give expansion histories A of t, which are interesting, which are inflationary, which are reasonable. And so you can do that by defining these dimensionless variables, x, y, and this tower of lambda m's, which you need to define. And you need to define them because the equations sort of demand them. If you look at the time derivative of x, that depends on lambda naught y and x, and this h dot of h squared depends on x and y. So the equation for x, the dynamical equation for x depends on x, y, lambda naught. That's the same situation in the case for the dynamical equation for y, but for the dynamical equation for lambda naught is going to depend on lambda naught x and y and lambda 1 and so on. And so you get this tower that forms that you need to deal with in some way. So it's an infinite open system. You need to close the system to make sense of the dynamics in a tractable way. So there's always the constraint x plus y equals 1, which is just the freedom equation, which we demand at all times. So then to extract a closed system of equations, you can, and to have a finite dimensional phase space, you can fix lambda m for some m greater than 0 to be some constant. You simply demand, you just simply set that to you. Okay, so then you end up with a constrained system of 2 plus capital M ordinary differential equations for all these variables, x, y, lambda naught, all the way up to lambda m minus 1. Those are dynamical. Lambda n you fix, and then lambda m plus 1 up to lambda infinity, so to speak, you can derive from the dynamical, solving the dynamical equations for that smaller finite subset of variables. Epsilon, the slow-roll parameter, is just 3x in the current constraint scenario, and so inflation occurs if and only if x is less than a third. So every time the system flows into a region where x is less than a third, inflation is occurring. You can see that once you plot, for example, the scale factor. So the two systems that I want to talk about are the zeroth order system and the first order system. These are the sort of two simplest phase spaces that you can set down. In the zeroth order case, you fix lambda naught, and you get a two-dimensional phase space, which depends on x and y, but there's a constraint x plus y equals 1, so the effective dimension of the phase space is just 1. For the first order system, you fix lambda 1, you end up with a phase space which is three-dimensional, but there's a constraint, and so it reduces the dimensionality to 2. And just to probe our intuition about single-scalar field models, if you recall, there was a transformation that you could make between CFT and lambda and LFT to write them in terms of the usual variables that we're familiar with. And if you were to do that in this case, then x refers to the fractional kinetic energy density, so it's interpreted in that sense, and y can be interpreted as a fractional potential energy density. These lambda m's you can think of as sort of the fractional sort of change in the nth derivative of the potential per unit Hubble time. Is the sort of interpretation you can give to it. And most importantly, when you fix lambda m to be a constant, lambda capital M to be a constant, so when you look to close the system of equations, what you've actually done is you've fixed a relationship between the nth derivative of the scalar potential in terms of the scale factor. So the nth derivative of the scalar potential becomes proportional to a of t to the minus lambda m. This is a strong sort of constraint that you set down, in effect, by closing the system of equations in the way I mentioned. So here's what some of the trajectories look like. Sort of the upshot at some level. The zeroth order system, you have, so I've plotted x against y, which is sort of here you have the sort of, you can think of this as a kinetic energy density, or a fractional kinetic energy density, y is the fractional potential energy density. The green dot is a fixed point, the red dot's another fixed point, and I've started these trajectories, so say in this case I've started the trajectory at x is 0.9, so the system is kinetic energy density dominated, and it flows towards this attractor. And it does so generically, it does so for every single value, because it's an attractor, it does so for every single value of these initial conditions. So there's a sense in which you can say that these kinetic energy dominated initial conditions, if you in fact think of the clock as a scalar field, generically flow into inflation. So for the first order system, the system is a little more complicated. The phase space is three-dimensional, and what you find, maybe we could just focus on this, there are these two fixed points. This turns out to be a saddle point, this turns out to be an attractor, these are two other fixed points. If you start from kinetic energy dominated initial condition, you will float, you will sort of skirt the saddle point and you flow into this attractor here. This down here is just a projection of the trajectory onto the xy plane, and plot the scale factor, right, with time. And so you can see that this looks like an inflating universe as you would expect once the value of x turns out to be less than 1/3. So there are other sort of trajectories which you can analyze as well, and in the interest of time I'll just point out one of them. If you start with a sort of negative value of lambda naught, so if you recall lambda naught was sort of the change, lambda naught will be the change in the potential, the fractional change in the potential per unit Hubble time, with a negative value, with a negative of that. So a negative value of lambda naught, you're actually set off your initial conditions in such a way that your potential is increasing initially. And that is a situation in favor of inflation, right? Inflation kicks in when you're potential energy dominated. And what you find in this case is that the system flows to the inflationary attractor, and it does so by these negative values of x. Right? So these negative values of x is something new that exists within this context of the effective field theory approach. Because x, if you recall, was c over 3m squared h squared, and c is a half phi dot squared. So c should be positive if you're dealing with single scalar field. But in this case, you can flow into negative sort of values. And so this is sort of a dynamics which exists expressly in the context of this EFT approach, which sits outside the usual single scalar field model of inflation.
Do you have any trajectories that go into limit cycles?
So not that I've seen, no.
It's always an attractor
or a saddle. Right, exactly.
Okay, I see.
Unstable fixed points too, so you get driven away.
Right.
But there are sort of non-hyperbolic fixed points at higher orders, which I haven't focused on a great deal.
So because if you could find a guy that goes round and round and cycles here.
Right. Yeah, and in that non-hyperbolic case that I'm thinking about, it's also a saddle. So
It is a saddle, okay.
Right, so then
Can you go back a slide? I just have a question. What in the upper left? What's the green point?
Oh, this
there?
is this here. That's a fixed point as well.
Okay.
Yeah,
But-
so that's a fixed point. If you start there, you'll stay there forever. It has a particular interpretation, which I'll get to in a little bit. So you can start thinking about these things in terms of single scalar fields, and you can show that this corresponds to, if you were to start there and stay there forever as a fixed point, this corresponds to a particular solution to Paolo inflation, so an exponential solution, and this in fact corresponds to this as well.
And the reds are saddle points?
These the reds are non-inflationary fixed points, and they'll have a variety of different.
And they're always 2 and 2?
So there are always, at most, 2 inflationary fixed points at any order, and they come in one of 2 varieties. And this is true for any value of n. And they take 2 single scalar field realizations, essentially, and I think that dictates the kinds of flows that you're going to be getting. I think it dictates, in some sense, the universality of the functional form of the phi that you get when you're dealing with trajectories in space. So then, I want to talk quickly about the probability of inflation for the first order system. So how is it that I think about this? What you can do, so this is the strategy. 1, you numerically find a portion of the phase space that corresponds to kinetic energy dominated initial conditions. That's straightforward. You know what that is by definition. The harder part is to look for flows that go to at least 16 folds of inflation or some amount of inflation. You're essentially looking for the basin of the attractor in this particular scenario. And then I set down a heuristic and specific probability distribution over all the possible kinetic energy dominated initial conditions. I'll just integrate over just the region which flows into inflation. And this gives me some sort of measure or sense of how probable it is to flow into inflationary states. And I treat 2 cases separately, one where lambda naught of Ti is greater than or equal to 0, and one where it's unrestricted. And the unrestricted case I set aside because of the fact that it favors inflation for the reason that I mentioned earlier. So in those 3-dimensional phase spaces that you sort of showed you earlier, I look at just the upper half in terms of the z-axis or the lower half, and the upper half of the lower. So one of those 2 cases. In this case, I'm just looking at the upper half, and so this is the basin of sufficient inflation. So everything that starts in here ends up over here, inflating forever, and then you can sort of set down a distribution, as it were, across the entirety of the space starting from the xy plane all the way to infinity, and I set down a Gaussian simply because it's tractable, and then you can vary the width of the Gaussian, and you can integrate over this region to show that, in fact, the probability of inflation, as I plotted it here, you can sort of ignore all the colors, just focus on the blue curve at the top, which corresponds to this particular basin of sufficient inflation. As I vary the width, as I increase the width, the probability drops, as you'd expect, with more of the support of the distribution is over initial conditions which don't in fact inflate. And as I narrow the distribution, the opposite happens. So this is a sort of heuristic way to probe the initial conditions.
You mentioned that you require 60 E-folds.
Yes.
But it looks like you have infinite E-folds.
I do,
right?
that's right.
So 60 is really not a useful constraint.
At least 60,
But
that's right.
does that affect the boundary? If you had said 45, would it have changed?
Yes. So there are, in the sense that there are also trajectories which will flow above so above this U, and flow into inflation and out of inflation.
Okay.
And they will have less than 60
And they'll finally
defaults.
end up in the red, one of the reds.
So what actually happens with them is an interesting question. I think you run into finite time singularities in the differential equation.
Okay.
So I haven't proven this to be the case, but numerically you can show it. Things are blowing up, right?
When you calculate the probability, you need some measure
Yes.
to assign
Precisely.
weight to different points.
That's
So
right.
is it, the question is whether uniform distribution in your coordinates is the right, or
Exactly.
any other.
Exactly. So I mean, I set down a Gaussian simply because it's easy to make sense of. It's easy to vary the width. And an important input into that choice is the standard deviation of the Gaussian. And I fixed the standard deviation to correspond to what I'm thinking of as a dynamically relevant region. A dynamically relevant region is roughly the average distance between all the fixed points. So this is the sort of region where interesting stuff happens, and so that's what fixes the standard deviation. It doesn't, I mean, in principle, right, it could be much larger, and this is what I'm looking at in cases here where the standard deviation is much larger than that particular quantity, and as you would expect, the probability. This is a sanity check. This plot, I think. Okay, and then when you include negative values, everything shifts up, and basically because there are sort of general arguments you can make that show that these negative values do generically flow into inflationary states, and so the probabilities shift. So let me then talk quickly about these sort of single-scalar field realizations. So I mentioned there are certain sort of initial conditions which lead to dynamical flows that can be mapped onto single-scalar field realizations, and some that can't because they go through, for example, a negative value of x. And in the case where you can, there is sort of, it'd be interesting to find out precisely what is the scalar potential that's underlying the dynamics. And there are two types of trajectories that are immediately interesting that you might think to analyze. One trajectory are those that correspond to the inflationary fixed points, so we sit at a fixed point forever, and two, where you start from kinetic energy-dominated initial conditions and you flow into the dynamically interesting region. So for the zeroth order system, and sort of what I mentioned earlier, that particular green dot there, if you stop there and stay there, you can map V and phi you can in fact show this analytically that V of phi takes that particular form. And phi and A are, U is a rescale time coordinate, and phi and A are the other parameters you would expect, other functions you would expect to extract from this analysis. If you flow, so if you look at a trajectory that starts from a kinetic energy dominated initial condition, flows into inflation, then you can fit your trajectory to that functional form that I've shown you on the bottom. This is a sort of universal functional form that I was talking about. And there you do sort of run into this sort of pseudo-Planckian values, as I mentioned, this was pointed out earlier. And of course, there's also issues where you may know that sort of exponential is parallel inflation is in fact a situation where inflation never ends, and so if this is the potential that's driving inflation, you need to append some sort of mechanism that stops inflation artificially. It's also something that's disfavored by the Planck data, so the values of NS and R, which we extract don't correspond to the Planck data. So in this sort of case, you would sort of think that this is a way to think about getting into inflationary regimes, and then we would possibly need to think about ways of getting ourselves out of them. At first order, the same sort of thing happens. That inflationary fixed point at the top corresponds to a particular solution to Paolo inflation, and the other fixed point corresponds to the single evolution. And again, if you look at trajectories with kinetic energy-dominated initial conditions, you will be able to fit that particular functional form. Again, and this is fairly generic. It's essentially the case for every single trajectory that I've looked at in all the various cases. Okay, so some general comments about higher orders before I conclude. So I mentioned this earlier, that at any order, there are at most two inflationary fixed points. And generally, one of them is sort of de Sitter evolution, or constant potential, and the other one corresponds to quasi-de Sitter evolution, sort of how the slow roll parameters not 0, it's less than 1. And it can be made to be close to 0. And then the single-scalar field realizations come in one of two varieties, namely de Sitter evolution, sort of constant potential, or this particular solution to Paolo inflation. And then to summarize, so what we've done to this point is that we've investigated inflationary trajectories in this sort of single clock context, finding that the probability of flowing into inflationary states for a sort of spatially homogeneous and isotropic background is significant for the two lowest orders of the system. If you include these initial conditions such that ensuing trajectories lie outside the usual single-scalar field realizations, they don't have single-scalar field realizations, you see an enhancement in the probability, i.e. there are more initial conditions which will lead to inflation, perhaps unsurprisingly. The trajectories that have single-scalar field realizations have this kind of universal potential that you can fit to the flows. And this may be related to the universal nature of the fixed points that I described earlier. And what we haven't done is to sort of tackle the question of how the universe gets into this, into a perturbed FRW state to begin with. Or starting from a perturbed situation, how you end up getting essentially rough homogeneity, is what I mean. So there's a sort of an additional issue that one could think about in this context. Okay, so that was all I wanted to say.
Questions?
What are the philosophical implications of your work?
I mean, I think there's a point to be made about this effective field theory approach, how general it is, the sort of power of this kind of approach. You can worry about the nature of fine-tuning in the context of effective field theoretic approaches, as we've sort of talked about in passing. It would be nice to be able to say something about the initial conditions problem by this approach. So if you include these higher order terms, you could make foundational statements, I think, about inflation and the march to inflation. If you could map some of these results onto some of these numerical analyses, which would be hard, and those are sort of here you have sort of small fluctuations, and what you really want to get is large deviations. It would be tricky, but if there were sort of limits that you could get to correspond to one another, there's some.
Mm-hmm. Yeah.
So the first order system,
Yes.
that's the one with just this single line, right?
Yes, the zeroth order.
That's the zeroth order,
Yes.
okay, this one. So you showed one trajectory,
Yes.
which is going towards the green.
Yes.
If I started to the left of the green, I presume it'll come in towards the green.
That's right.
It's an attractor.
Exactly.
But does it mean that there is no trajectory that will end up on the red?
That's right. In this case, because the red is an unstable
It's an
point.
unstable thing. Okay.
Yes, and so
that means that for this particular problem,
for this
regardless of initial conditions, it will always be inflationary.
in this particular situation, that's right.
100%.
100%. For various values of lambda naught, which I fixed. But yes, and if you start from the left-hand side of the green dot, you're sort of starting from a potential dominated situation to begin with, so you expect inflation to occur in that situation.
Right.
However, right, I mean, if you start here, to the right of this red dot, you flow into a finite time singularity away from the situation.
Okay.
So it's not 100%.
It's 100%
It's
in
100%
this quadrant.
within what we would think of as kinetic
the
energy
reasonable.
dominated initial conditions. Yes.
Okay, I see.
Yes.
Okay.
Right, so it's a neat sort of idea, but things go, it's a little trickier when you go to higher orders because the degrees of freedom increase and things can happen.
Okay, thank you very much. Right at that. Alright, so our second speaker is Paolo Pani. He's a professor from the Sapienza University in Rome. And I think he knows the people here because you were visiting this CFA, right?
2013. Yes.
Right. And Paolo works at the intersection between gravity, particle physics, and astrophysics. And today he will tell us about new physics at the horizon scale with gravitational waves.
Thank you. So thank you very much for this invitation. It's a pleasure to be here. As she was saying, I visited Javi in 2013. We were working about primordial black holes at that time. It was not that fashionable as it is right now. So today I would like to talk about something else, namely how to test the nature of compact objects, of dark compact objects with gravitational waves, and looking for signature of new physics at the horizon scale. Let me just start by something that all of you will be very familiar with by now, which is the gravitational waveform from the coalescence of two dark compact objects. So here I'm showing the first signal detected by LIGO, and is typically divided in three parts: the spiral, the merger, and the ring down. And I will claim that these three different phases provide complementary diagnostic to the nature of compact objects, so they provide independent tests. What is interesting here is that from the spiral phase, one can infer that the two objects had a masses about 30 solar mass each for the first event, and because of the very high frequency, merger frequency, we can infer that when they merge, they were very close together. So essentially, they were within the common envelope of a few Schwarzschild radii of the final object. So definitely, this signal shows the coalescence of two very dark objects, which are way more massive than neutron stars. And the most natural explanation is that they are two black holes coalescing and forming a final distorted object that vibrates in the so-called ring-down phase. However, I will show you that even in this situation, there is room for interesting new physics to look at and to constrain. So let me put it straight. Of course, black holes are consistent with all observations so far, including gravitational wave detections, and they are very economical solution. In fact, they exist with arbitrary mass, which is very important because we want to describe both stellar mass objects and supermassive objects. They have a compactness of order 1, they are easy to form in dynamical situations, and they are linearly stable. On the other hand, they also have a lot of theoretical and philosophical problems that might be of interest particularly for this institute, which is multidisciplinary. In fact, they harbor a curvature singularity where Einstein theory breaks down and loses predictability. They also harbor closed time-like curves where causality breaks down, and they also harbor Cauchy horizons when the initial value problem doesn't make much sense. So usually these problems are dismissed by the fact that they are hidden by an event horizon, so they are disconnected to our exterior. However, this also shows that event horizons are in fact required for the self-consistency of general activity, so they are a very important ingredient in the theory, and we should put a lot of effort in trying to test whether they really form or not. And even if they do, they come with their own set of drawbacks. For example, they have huge entropy, some 20 orders of magnitude larger than the stellar progenitor. They are associated with the infamous information loss paradox, and to the fact that black holes are thermodynamically unstable. So I think there is a lesson to learn. I like to always draw this analogy with the development of electrodynamics. So since Maxwell theory, we know that the electric field near an electron is divergent, and such a divergence is being resolved by quantum electrodynamics by introducing new structure near the electron, such as vacuum polarization. Likewise, the singularities inside black holes might be solved by quantum gravity by changing the structure near a singularity, but they might also, like in some approach, be resolved by giving away completely the horizons. And in fact, there are all these classical solutions that usually I call exotic compact objects or ECOs, which essentially are objects predicted by general relativity or other theories, which have all these nice properties of black holes without having a singularity or an event horizon. So I think it's important to classify exotic compact objects by compactness, by their compactness, because there are objects which are exotic but not such extreme. For example, boson stars. Boson stars are condensate, scalar condensates allowed in in Einstein theory with a scalar field, they can be more compact than neutron stars, but way less compact than black holes. So they, in this diagram, they lie somewhere over here. When they are very compact, they might even have a photosphere, so they will have a very similar shadow than black holes, but they are not as compact as other objects that are in this diagram here, which we usually call CLIFOs, because they have a clean photosphere. That is a technicality that is not important here. But for these objects, the surface of the object is located just one Planck length away from the would-be horizon, and these are all motivated by quantum gravity scenarios. So in the rest of my talk, I will parameterize the surface of the object by this parameter epsilon here. So the surface will just be an epsilon away from the would-be horizon. And for Planck scale correction, this epsilon is about 10 to minus 39, 10 to minus 46, depending on the mass of the object.
Can I ask a question?
Sure.
When you talk about exotic compact objects, is the idea that they can explain both stellar mass black holes and supermassive black holes? So a boson star could be 4 million solar masses, but also a few solar masses?
Boson stars can be, but for a given set of parameters, they only explain one of the two. So essentially, well, I will show you probably in one of the last slides. So the scalar field has a mass term, and depending on the mass of the scalar field, they can be either, say, stellar mass objects or supermassive objects.
But they can't be both. Are there any of these that can be both?
It's really, well, in this case here, the idea is that there is no scale at which these effects take place. So they will form both for stellar mass or for supermassive, in principle. I mean, one of the big problems that we mentioned in the end is there is no formation, really stable solid formation mechanism for this. But yeah, the proposal would be that. Okay, so I was mentioning before to Naresh that some of these objects are not ruled out by observation. Recently, there was this very nice paper showing that objects here in this around this region here are ruled out by stellar destruction events, so the absence of very high luminosity in stellar destruction events. However, all these classes here motivated by quantum gravity are not ruled out by current observations, and in fact, it would be very difficult to probe these objects with electromagnetic observations, because essentially they have the same geodesic structures around outside the surface of a black hole. So what I'm interested in is trying to understand whether we can use gravitational wave observations to test these exotic objects and perhaps ruled out some new region in this parameter space or find evidence for new solutions. So in the first part of my talk, I'll discuss ring down tests. So basically the post-merger phase of the ring down of the gravitational waveform, and I'm going to discuss work mainly done in collaboration with Vitor Cardoso and many other people occasionally. So very briefly,
what does it say? Was it French?
Yeah, this is French. This is not a black hole.
Okay.
Yeah, I think it's one of Marguerite. This is not a pipe. What is this? Well, there is a famous portrait. Well, yeah, because I'm going to claim that this signal can also occur at least for a certain amount of time, also if the object is not a black hole. And the way I'm going to analyze this is by looking at the ring down part here. And the ring down part is typically modeled as a superposition of a quasi-normal modes of the system. So the final object vibrates with proper frequencies. These are the quasi-normal modes of the black hole. And this part is a superposition of these damped sinusoids, because they have a damping time, so they are complex frequencies. So the idea is very simple. Usually people look at this ring down part, extract the frequencies, and because they match the Kerr quasi-normal modes, we can exclude other objects. I will show you that this is not that easy. And before doing that, for those of you who are not familiar with quasi-normal modes, let me just give you a one-slide presentation on this. So Einstein equations linearized on a curved background takes this Schrödinger-like equation there with an effective potential that I'm showing here for a Schwarzschild black hole. So this potential goes to 0 at minus infinity. In this coordinate, the horizon is at minus infinity and the asymptotic infinity is at plus infinity. There is a maximum here which roughly corresponds to the photon sphere. So the quasi-normal modes are the complex eigenvalues of this problem once one requires physical boundary conditions, which in this case are that nothing comes out of the horizon and nothing comes in from infinity. And this selects complex frequencies. The real part of the frequency is the oscillation frequency. The imaginary part is the inverse of the damping time. So what happens if you remove the horizon? Whenever you remove the horizon, you will get something like this. So a sort of interior that has a stellar-like structure. There will be a centrifugal barrier. So you immediately find two things. First thing is that the boundary conditions will change completely. So this will change drastically the quasi-normal mode spectrum. And also, you can have trapped modes within the centrifugal barrier and the exterior. So the exterior in the two cases is the same. What changes are the boundary conditions at the horizon or at the would-be center of the stellar-like object. And in fact, if one computes the quasi-normal modes of an exotic compact object and compare them with those of a black hole, they are completely different. So here I'm showing the real part versus the imaginary part of the mode. These dots are for the Schwarzschild quasi-normal modes, and these are for an exotic compact object. The interesting thing is that the black hole limit, so this is for different compactnesses, and the black hole limit is down here. It's a logarithmic scale, which means that the more the object is closer to the black hole, the more different the quasi-normal mode spectrum is. And then you may say, okay, but then it's very easy to distinguish the two of them, the two, because, well, here are order 1 corrections. So if we extract the quasi-normal modes from the signal, say, in LIGO data, we may, of course, rule out this object. In fact, it's not that easy, and let me show you why. The reason is that we actually observe time domain waveforms, and those are more tricky to deal with. So to illustrate this problem, let me do a Gedanken experiment. So we'll take a point particle, and this is plunging toward a black hole, a Schwarzschild black hole, and I will take the same particle plunging into a wormhole. So the particle goes through the throat and emerges from the other side of the wormhole. Of course, this is only an illustration, but I want to show you that if you look at the gravitational waveform within general relativity, what you find is that initially the two waveforms are exactly the same. So you'll see the standard ring-down signal, both in the black hole case and in the wormhole case. So these are actually two curves on the top of each other. And in the black hole case, what you will find next is nothing. So the black hole, the signal dies off exponentially, and all you get is this ring down here, which has nothing to do with the horizon. It's just a generic property also of the wormhole case. In the wormhole case, however, if you wait long enough, what you see is that a secondary mode appears after a delay time that is related with the time radiation takes from the fallen sphere to the center of the object and back. Interesting enough, this delay time scales logarithmically with the compactness. It's really just the time dilation effect. And this is interesting because it means that the surface can be, or this throat, can be very close to the horizon, and because of this logarithmic term, the time we have to wait before seeing this secondary mode is not that long. And because, well, all talks about gravitational waves are not cool enough if you don't play waveforms, I play this waveform for you. And you see why they are called echoes. Well, we called them echoes because, in fact, they are just really the echoes of the radiation. It is reflected from the surface of the object or the center and goes back and forth. So what they do is they essentially, where do they go back? They essentially are bouncing back and forth this potential barrier here. This potential barrier. So they are bouncing back and forth. Eventually they do tunneling from times to times. And so the time scale that you are seeing here is really just the time that light takes to go back and forth.
There is no reg.
There is basic, well, if you wish, this is, no, there is no regime in this case. So this is really the time, well, it's the proper time.
So this object, the surface, do you have to decide on the boundary condition there? If you have any freedom, what boundary condition you put?
You do have freedom. In this particular example, I'm essentially considering perfect reflection because there are certain models of quantum gravity which say that below a certain frequency given by, say, the quasi-normal mode frequency, all radiation should be perfectly reflected. Of course, you might have different conditions. for example, in the gravastar case, you will have radiation going in the interior, and then it will interact with the matter in the interior, and then it will be bounced back. So it depends. It's model dependent.
And that will change the.
It will change, but not dramatically. In particular, it will not change the amplitude of these modes, because one may say, depending on the model, this amplitude can be negligible, but in the end, this amplitude is related with how much energy is reflected by the photosphere barrier. So that is sort of universal. So I find this interesting for the following reason. Usually in quantum gravity, there is this common law that any quantum gravity effects is suppressed by powers of Planck length to the Schwarzschild radius. And if this were the case, forget about testing this with astrophysical black holes, because this number would be tiny. But this is a counterexample of this. So this is a part of paper taken by, written by Samir Mathur, the proponent of the Fastball proposal. And I find it interesting that this is a counterexample showing that a logarithmic term can save the day in this case, giving a delay time that is within current observations. And in fact, after our paper, some groups took it seriously, and in particular a group at the Perimeter Institute. And what they did was to take our model and look whether there was some evidence for echoes in LIGO data. So what they did was to take the time series of LIGO data, shift it by the echo delay time for the different events that were available at that time, because the echo delay time depends on the mass and spin of the object. And well, they tried to accumulate evidence for the existence of echoes. This is a very controversial paper. They initially claimed a 2.9 sigma significance. This was criticized by this group here. They replied back. So the situation is unclear. I can tell you that starting from tomorrow, there is a workshop on precisely on this issue at the Perimeter Institute. I'm going there, and I think many people will discuss these ideas. And the interesting thing, though, is that in the last year there's been a lot of progress in modeling the gravitational wave echoes. There are a bunch of interesting papers, especially this one by the Caltech group, Mark et al. It's very interesting. What I would like to stress, so regardless the existence of the significance or not, perhaps it will fade out. But the interesting thing is that even posing this question, so whether there are hints of quantum gravity in LIGO data, is something that is, I think, remarkable and unexpected since a few years ago. Okay, so in the second part, I would instead like to discuss the in-spiral waveform. So this was the post-merger ring-down waveform. How about the pre-merger in-spiral phase? And the motivation is that most of the signal that LIGO will see in the future will be like this one here. So with a very long in-spiral and almost negligible SNR in the ring-down part. And so it is important to try to model even tiny correction in the spiral phase, because they will accumulate cycle by cycle. Of course, this is a different game, because one requires to extract very small corrections from the data, but it's something that can be done, as I will show you now. So the idea is very simple. The in-spiral phase can be modeled analytically in a post-Newtonian expansion. So it's an expansion in v over c. V is the orbital velocity, c is the speed of light. And the waveform looks like this one here. So we are interested in the phase. And the phase can be divided roughly in three parts. So the first one is what people usually call point particle phase. So in this phase, the objects are modeled as 2 point particles with some multiple moments, and they interact gravitationally. And this is done, so there are powerful techniques to do this order by order in the post-Newtonian expansion. So up to 1.5 pn order, the waveform depends only on the mass and spin of the two objects, meaning that if these are black holes or something else, the waveform will not see any difference. But to second pn order, there is a term depending on the quadruple moment. And this is important because it allows to do a Noether-Thiern test of the Kerr black hole, because for a Kerr black hole, the quadruple moment is written uniquely in terms of mass and spin, but for an exotic compact object, it is not. So one can try to measure the quadruple moment of the two components and see whether it agrees with Kerr or not. This has been done recently in this paper here by Arun and collaborators. There are some limitations, though. One is that this effect is quadratic in the spin, and because the initial component, at least of the events we have seen so far, have a very small spin at most, this effect is suppressed. And also, for many exotic compact objects, especially those that modify the black hole horizon at the Planck scale, the quadruple moment is approaching that of Kerr, not as a logarithmic term, but as a power law. So basically this means that these corrections to Kerr are negligible in this case. However, there are other corrections in the post-Newtonian phase which are more interesting. So one is the tidal heating. So tidal heating is essentially the fact that the horizon can absorb radiation, so the binary proceeds not only by emitting gravitational waves to infinity, but also absorbing radiation at the horizon. And of course, if you don't have an horizon, because you have, say, a gravastar or whatever, you will not have this term in your post-Newtonian expansion. This term is at 2.5 pn, so it's small, but it's only linear in the spin, so it's not suppressed for highly spinning, for slowly spinning objects. And recently what we were studying is whether this effect can be detectable in future data. So LIGO probably will not sensitive enough for this effect. We were looking at the future LISA mission that I also mentioned before. This is because, well, supermassive black holes will provide a much higher SNR. And what this plot shows is the observational error through a Fisher matrix analysis for a supermassive binary of equal mass, of equal spin components. And so essentially all these data below these lines provide a measurement, an error measurement that is within one sigma, allows you to distinguish between a case in which there is a tidal heating or there is none. So essentially all these points here at very high spin will allow to distinguish between black holes or exotic compact objects on the basis that in one case there is no tidal heating and in the other case there is. Finally, there is another correction, it's called tidal deformability, and this has to do with the fact that these objects are in fact not point particles, they have finite size, and therefore the quadruple moment of one guy is deformed by the tidal field of the other guy. And this enters in the waveform to 5th PN order, so it's a tiny correction, proportional to the so-called tidal log numbers that you might have heard of in astrophysics. The interesting thing is that there is a beautiful theorem in general relativity. It was proved by Thibault d'Amour and independently by Eric Poisson and their collaborators. And this theorem shows that the log numbers of a black hole are precisely 0 in general relativity.
What is a tidal log number? What is this?
So the tidal log number is essentially the induced quadruple moment per unit of tidal field. So if you have a binary, this guy will induce a quadruple moment on this guy while they are orbiting, and the ratio is basically the tidal log number.
Love was the person.
No,
Love is a
I
person,
understood
yes,
that.
yes.
And but the and it doesn't include effects on accretion or anything like that. It's just the pure.
Yeah, it's just
objects.
here, just two finite size. Actually, a finite size object and a point particle, say, or a tidal field. And the interesting thing is that for black holes are 0. So a black hole, the horizon is deformed by a tidal field, but the quadruple moment is not. So the tidal field is 0. On the other hand, we recently showed that for exotic compact objects in this Planckian limit, the log numbers are non-zero, but they scale logarithmically. So again, there is this logarithmic.
Is that somehow because you can't get a black hole to radiate by putting an object around it? Is that what that is? Because the radiation would be the time derivative of the quadrupole moment, right? So, is there a reason for that? The star would get a quadrupole moment. Right?
The star will have a log number, yes. The black hole, it has to do somehow with the Noether theorem, but it's a sort of Noether theorem in non-asymptotically flat spacetime because there are sources at infinity. So I'm not sure whether it is related with because a black hole will radiate, right? In which sense they will not radiate? Say if it's in a binary system, it will. Right?
There's a binary system already. Yeah.
I mean, somehow it's related with the fact that, say, it doesn't have scalar charges, but not quite. So anyway, my point is that these log numbers for exotic compact objects are non-zero, they scale logarithmically, which means that even if this object is Planckian, this number is not ridiculously small, it's about 10 to minus 2. This is a dimensionless number. For a comparison, for a neutron star, the log numbers are about 10 to 2, so this means that this is 4 orders of magnitude smaller than that of a neutron star, but still is something which is measurable in the future, as I showed here again for the LISA mission. So very highly spin binaries, supermassive binaries, will be able to distinguish between having a non-zero log number for the components or not. Finally, before I conclude, if you're interested in boson stars are much less extreme objects than those that I was mentioning before, so they are somehow easier to rule out. For example, they have a big love number. They also don't have tidal heating, so it's easy to distinguish between the two of them. And boson stars depend a lot on the cell potential that you consider. So this is why before I was mentioning that they have a mass term, but they also have, say, quartic potential and so on and so forth. They might describe stellar mass object or also supermassive object, depending on these parameters here. And this analysis done recently, earlier this year, shows that LIGO can distinguish between black holes and boson stars in the case of less compact models, which are these two, is called minimal and massive. But the solitonic one, which is the most compact, is still compatible with LIGO. In the future, third generation detectors and also LISA will be able to distinguish and to essentially rule out or detect boson stars essentially for any model, which I think is something interesting. So to conclude, I hope I convinced you that gravitational wave astronomy provide new opportunity to test new physics at the horizon scale. I think that the ring down and the spiral part are somehow complementary in the sense that the ring down provides smoking gun effects such as gravitational wave echoes, which are not present for black holes but are present for exotic compact objects. The spiral part is different because it requires precision effects, so time effects, to extract time effects from the signal, but it's also interesting because there is a series of null test hypotheses that we can do. For example, black holes have tidal heating, but exotic compact objects do not. Exotic compact objects, on the other hand, have a love number that black holes do not, so we can try to extract this signal from this information from the signal. I didn't talk much about merger because there are very few simulations of exotic compact objects. There has been recent progress on boson stars. Carlos Valenzuela, Luis Lerner, and others are working a lot on this. But again, boson stars are not as extreme as other objects, so there is a long way before we understand the merger of two exotic compact objects. And I think a take-home message that highly spinning supermassive binaries for LISA would provide unparalleled test of quantum gravity at the horizon scale, which is very interesting. So they will provide to test all these properties here. There are many open problems. If you are interested, we can discuss them later. Formation of most of these objects is unknown. They might be unstable when they rotate, so there is this instability is called ergo-region instability. And well, they might be unstable depending on the parameters. One prediction of this instability is that exotic compact objects should be slowly spinning, and this is, by the way, compatible with LIGO observations so far, but it's not compatible with X-ray sources, so it's something to understand better. And we are still missing a full coalescence waveform for exotic compact objects, which will be important to do a full test, spiral merger ring down test of these ideas. So you might think that this is very exotic, and perhaps it is, but I like to remember that even pulsars were completely unexpected before the radio astronomy revolution, so I will not be surprised if in the future we will detect something like this. It took me a lot of time to do this, so this is why I always choose. Yeah, thank you for that.
I want to go back to this boundary condition business. So all of these echoes and everything, you want the signal to bounce back from the surface. Suppose I just told you, I have an exotic compact object. And for some, anyway, I know nothing about this object, and I just tell you, this object will just absorb anything that falls on the surface. Nothing is reflected. All of these signals will go away, right? Except, I think one of your love number probably will still have some effect, but other than that, all the other predictions will be wiped out.
Right.
Okay.
But if the object absorbs any radiation, I would call that an horizon.
No, that's the thing. This is not a horizon, it's a gravastar. But it's a very special gravastar. It just absorbs everything.
Yeah. Or which kind of
Once I'm making up stuff, I can make up whatever I
No, that's right. Well, but say a gravastar is made of fluid, right? And
Yeah,
fluid
but it
will not
absorbs.
absorb. Well, absorbing gravitational waves is hard.
That's a good point, yes.
No, but anyway, you're right.
Yeah.
In fact, in this paper, so I was mentioning the instability, right? I think I have some backup slide here. I was mentioning the instability, and because the instability is a big problem. I me see if, yeah. When these objects rotate, they are unstable. And what we were looking with my student here is, what if this surface is not perfectly reflecting, there is a small amount of absorption. And what this plot shows is that, so this is for perfect reflection, and if you allow for, say, 0.4% of absorption, this mode that is unstable here because it's positive goes on the other side, so the instability is completely quenched by this small amount of absorption.
So small amount of absorption is good. It
Small
makes
is
it
good.
stable and it will still give
Right.
you an echo.
Right, but
100% absorption
is not good. Right.
Okay.
So when two such objects collide, there must be some modes excited very violently in this spin. One is imagining.
Some matter mode, yeah.
Yeah, and that would change the gravitational wave form, right?
Right. If there is enough, so if the matter is enough compact and and are relatively.
But that's not included in the.
It's not. This is
that's-
not.
That would be dramatic.
Get a kilonova.
Yeah, probably you will get some electromagnetic
Exactly.
counterparts.
So
right?
we don't see it. Like why not use that as a little constraint?
Yeah, it could also be that, for example, it might be highly redshifted. The problem is that we don't have any of these simulations to be sure that there is this signal.
But that is a different type of signal.
Right, yeah. And also the gravitational waveform would be different, perhaps, like in neutron-sun binaries, it would be like a post-merger structure. It's not present.
It seems to me like this would be the most obvious thing to look for.
If it is baryon. Problem is, these exotic models, we don't know what it's made of. So it
No,
may
but
be
you make the black hole out of baryonic material, right? To start with, a collapse of a star, let's say. So then you want to convert it to some exotic form of material.
Yeah.
I mean, how is that
That's-
possible? By baryon number conservation.
No, but this is the usual way the game is played.
They
You
violate.
allow yourself all sorts of new equations of state, new types of matter, whatever, just to avoid forming a horizon.
So you violate baryon number conservation. Okay. But that's a quite dramatic quantum mechanics.
Yeah, so
Yeah.
I had a comment of like a real world observational comment, a little bit aside from the fact that I don't know how to make these things, right? And maybe there is some way of making them that, you start with a black hole and it transmutes into something
Yeah,
else.
but I think it's fair to say that nobody knows.
Nobody really knows.
Yeah.
But if there is a way of making them, then it has to be ubiquitous, right? I mean, you have to make these kinds of black holes everywhere because we think there are many black holes in the universe, right? So there has to be some real production line mechanism to make all these exotic objects, right?
Right.
But then there's the point that Ramesh has done a lot of work on like total bolorimetric luminosity and the fact that when you actually accrete gas onto a black hole, it has to go somewhere, and there is advected through the event horizon, and that explains the low luminosity for a whole class of supermassive black holes. Or it builds up on the surface, and you would see it glow. Right. So how strong is that argument against some of these exotic
Right.
objects? Because
So-
there's more than one way to rule out exotic objects.
So as I was mentioning at the beginning, some of these arguments ruled out objects which are very compact, much more compact than, say, the photosphere location, but not quite as compact as say, Planck scale correction at the horizon. That is what these models are supposed to describe. The argument which sort of soften these electromagnetic bounds is the fact that suppose that you have radiation, matter that goes onto the surface, and perhaps, one of the arguments is that if it is in thermal equilibrium, all the matter that will go in will eventually go, all the energy that will go in will eventually go out. But what happens is that if the surface is very close to the horizon, most of the radiation, so there will be a very small escape angle for photons to escape to infinity. So most of the photon will actually bounce back here on the surface, be reflected back and forth. So if one computes the time scale, is actually much longer than the Hubble time scale. So this means that it will never thermalize. And this set a bound on the compactness of the object. So if it is too compact, it will never thermalize, and these arguments on the bolorimetric luminosity will not apply. But on the other hand, if it is compact but not that compact, they will deconstrain it. You see what I mean?
Kind of. It seems to violate something there. So you're saying you can make a virtual horizon that's just epsilon bigger than.
No, what I'm just saying is that an amount of energy takes a very long time to escape to infinity. This is what I'm saying. And this is because it will only a very small fraction proportional to epsilon will escape to infinity after the first, say, time that it hits the surface. All the rest of the energy will bounce back because it's so it will try to escape, but it will bounce back because of the gravitational attraction, will hit the surface again, but only a small fraction of that energy will eventually make it to infinity. So if one computes, the time scale for this process is very long. It actually goes like m over epsilon. And if epsilon is very small, this time scale is huge.
Okay.
That's a way to avoid the constraints that Ramesh derived.
So the idea is, if you really wait long enough, yes, whatever went in will come out. How long do you have to wait before it reaches this steady state balance? For a Planck length, it does take a long time.
Yeah, but doesn't that mean that all the energy has to get that close to the surface?
It's still stuck between the surface and the photon sphere, basically. It's kind of bouncing around because the escape angle is so small. It bounces a zillion times, and then once in a while the guy escapes. That's all that you observe. And then after a long time, it will reach steady state. But I think what Paolo is saying is that if your epsilon is like the Planck scale, then this time is really long.
Okay, Marles and Paolo again. I think
So we have pizza at 4:30, but is there is a LIGO Journal Club when? At 3, yes. So in 20 minutes.